Hello, everybody. Let us begin by looking at how combinatorial optimization connects to quantum computing. Many real problems in networks, logistics, and data science can be framed as choosing the best configuration among an enormous number of possibilities. So, if there are a number of possibilities are there, you have to choose the best solution from the set. Now, classical computers often struggle because the search space grows faster than any practical algorithm can handle. Quantum computing offers a different way to model these problems by translating them into energy minimization tasks. Now, in this lecture, we will use MaxCut as our running example. It is simple to state, deeply useful, and it shows how a graph problem can be rewritten as a Hamiltonian that a quantum algorithm try to minimize. Now, this connection between the combinatorial optimization and the quantum computing helps us understand why quantum devices are being explored for optimization and how methods like QA/OA or QUBO build on this type of formulation. So therefore, our goal today is to build this bridge step by step so the shift from classical thinking to quantum modeling feels uh, very natural. So let us try to understand the combinatorial optimization problems and how these problems can be mapped to quantum computing. And as I said, we will take the example of the MaxCut problem. Let us consider MaxCut problem for this mapping. Split the vertices. So we are given a graph. A graph will have vertices and edges. Split the vertices of a graph into two groups. I'm trying to define the MaxCut problem. So split the vertices of a graph into two groups so that as many edges as possible go in the two groups together and not inside single group. So that means we have to create two groups of vertices, right? And split the vertices of a graph into two groups so that as many edges. So when we will create an edge, the edge will consist of a vertex from one group and a vertex from the other group. So those edges we are looking for, and we have to maximize those types of edges so that one vertex will be from one group, the other vertex will be from the other group. That's what that's what actually defines the MaxCut problem. So let me define once again. Split the vertices of a group into two groups so that as many edges as possible go in the two groups together. So we will consider those edges where the edge will go in both the groups, not inside the edge should, we will not consider those edges which remain in a single group. That means the two vertices cannot be from the single group. We will consider those edges where one vertex is from one group, the other vertex is from the other group, and we have to maximize that number. So this problem is known as maximum cut problem or max cut problem. So MaxCut is the arrangement with maximum number of disagreeing neighbors. Disagreeing means when we are creating two groups. So one group and the second group, we are considering those two groups as disagreeing neighbors. So MaxCut is the arrangement with maximum number of disagreeing neighboring spins. So neighboring spins means let us for the time being understand the vertex only in terms of, let us understand the spin in terms of vertex. So maximum number of disagreeing neighboring vertices, which is basically the same as minimum energy of a certain Ising model. So why I'm mentioning spins here, because we have to look into the classical Ising model. In that model, we will consider the magnetization of the particles, and therefore the spins of the magnetic particles will build up into a classical Ising model. So for the MaxCut problem, we have vertices, and the edge will consist of the vertex from one group to the other group, and we will try to map the MaxCut problem to a classical Ising model where the spins of the particles will be our target. So let us try to see how this can be done. So let us consider a graph with V as the vertices and capital E as the edges. So V is the set of vertices, E is the set of edges. So I comma j are the indices, right? Which are the indices which define the vertices. So I is a vertex also, and j is also j is also a vertex. So I comma j. So both the vertices are from this set consisting of vertices. Right. Now, W subscript ij is the weight of the edge joining vertex I with vertex j. So it has to be greater than or equal to 0. So weights for each edge. So what is an edge? Edge will consist of a vertex I joining vertex j. So this is the set of edges, and if the uh, weights of the edges are 1, we will say that this is an unweighted graph, right? Otherwise, if the vertex I is joining vertex j, so it may have a weight other greater than or equal to 0. I mean, any value can be there. If it is 1, then we will say that the graph is unweighted. So all in all, the problem is that we have a set of vertices, we have set of edges, right? So an edge is basically joining the two vertices, but we have to consider those edges where the two vertices are from different groups, and we have to maximize that number. In maximizing that number of edges, we are actually trying to maximize the weight. We will see how. Now, a cut of the graph is a partition of V into two disjoint subsets. So we have to consider, we have to create two disjoint subsets of V, right? That will be called as a partition. And who will do it? A cut will do. We will put a cut onto the edges, right? That cut will create the whole set of vertices into two disjoint subsets. Now, this set of all the vertices is the union of the two groups S and S bar, and the intersection of the two disjoint groups will be a null set, right? The cut set is the set of edges with one endpoint in S and the other endpoint in S bar. So two sets are there. One we are calling it as S, the other we are calling it as S bar. So what is delta S? Delta is the set of edges which with one endpoint in S and one endpoint in S bar. Now the size of the cut, if it is unweighted, is the magnitude of this number delta S. So what is delta S? Is the set of edges, right? So how many edges will be there? If we take the absolute value of this delta S, so if it is unweighted, that means we are not considering weight, then the number of edges will give me a number. If that number is maximum, So our solution to the max cut problem is this number mod of delta s. But if it is weighted, if the graph is weighted, then uh, we will consider all the edges and we will consider their weights. So once all the weights are obtained, then we will sum all the weights and that will be our size of the cut. So if the graph is unweighted, what is the size of the what is the cut size? Maximum cut size is the number of edges. If the graph is weighted, then what is the cut size, or the maximum cut size is the sum of all the weights of those edges which create a max cut, right? The max cut problem, given a graph with the weights w subscript ij greater than or equal to 0, we have to find a subset S that maximizes cut S. What is this cut S? Cut S is the summation of the weights which are actually creating a max cut. So we have to maximize this summation of the weights, or equivalently find a partition that cuts edges of maximum total weight. In other words, we can say it like this also. So let us formally formulate MaxCut to be used in combinatorial optimization, Kubo and Ising model. So all these things are related. So till now we have understood the MaxCut problem, which is a combinatorial optimization. So combinatorial optimization means we have a combination of the solutions, right? So that solution we have to consider, which gives me the maximum, which is a max cut basically. Now this is a 0-1 variable solution, variable formulation. Let us see how. Now what we will do is we will assign a binary variable xi to each vertex. So we will assign a binary variable. So by this binary variable will be either 0 or 1 to every vertex of this set V. We will assign 0 to the vertex if it belongs to capital S, and we will assign the vertex, the binary variable 1 to the vertex if it belongs to S bar. So that's how the 0-1 formulation is done. Because in the MaxCut problem we are creating two disjoint subsets. One is S and the other is S bar. If the vertex belongs to the subset S, it will be designated as 0, and if the vertex is from S bar, it will be assigned a binary variable 1. So that's how it is a 0-1 variable formulation. Now for an edge, let us say the edge is I comma j. So how this is an edge? Vertex I joining vertex j. So this makes an edge. So when is it cut? Right? The edge is cut if the endpoints are in different subsets. So we will consider that edge as cut if the two vertices belong to different subsets. That means xi, which is the starting vertex, and xj, which is the end vertex. So if they belong to different subsets, that means one vertex will be from S, the other will be from S bar. That means it has to say that 0 is not equal to 1 basically. Now this square, so let us understand how this problem can be formulated using the square bracket. Now the square bracket notation, let us say I'm just trying to explain the square bracket notation with the example of expression P. Now if P is the expression which is inside the square bracket, so the square bracket notation is used as an indicator function, also called inversion bracket. Now what does this function state? So P inside the square bracket is equal to 1 if the statement is true, if the statement P is true, and it is equal to 0 if the statement is false. Now in our case, what is the statement? We will use this statement xi is not equal to xj. So what we are doing here, we are putting a statement xi not equal to xj in the square bracket. So this is our indicator function, correct? So what is this? Now if this statement is true, that means if xi is not equal to xj, then the output of this square bracket or output of this expression will be equal to 1, right? And if uh, this statement is not true, then it will be equal to 0. Okay, so when xi is equal to 0, xj is equal to 0. That means both the vertices are from the same group. So output should be 0. In this case, we are considering this expression xi plus xj minus 2xi xj. So this is our indicator expression that we have chosen. So let us see whether this expression that we have chosen is correct or not. So if xi is equal to 0 and xj is equal to 0, that means both the vertices are from the same group. So 0 plus 0 minus 0 will be 0. So it is not a cut. When xi equal to 1, xj is equal to 1, again it is not a cut because the two vertices are from the same group. But if xi is 0, xj is 1, that means the two vertices are from different groups. Then if you put the values of xi and xj in this expression, you will see that the answer will come out to be 1. So therefore it is a cut. And in the other case, if xi is 1, xj is 0, again it will give an output of 1. So it will be a cut, right? So this expression actually explains the whole MaxCut problem. So therefore the cut weight can be written as, so how the cut weight can be written as? Now this is the expression. It will give, this expression will give an output of 1 or 0, right? If we multiply it with the weight of that edge, if the edge weight is 1, so it will be, the value will be either 1 or 0. But if the weight is, if there is a weight, right? If the weight is 1, in that case, the number of edges will give me this cut weight or cut x value, right? Because the number of edges will be equal to cut x. If let's say the number comes out to be 5, my cut x value will be 5 if the weight is 1. But if the weight is not 1, but it is something else, but greater than or equal to 0, in that case we have to multiply this expression with the weight of that edge. So we take the sum of all the edges which come for the MaxCut, right? We sum all the weights, then we get this cut x. So that will be the, so from here we can find out the cut weight, that means the MaxCut weight, that means the cut for which we get the maximum edges, so we can find out. So this is our, this expression cut x will give me the weights of different cuts. So some cut may be, only one cut will be a MaxCut, but there can be other cuts which may not give the maximum value. So in that case, this cut x is basically the weight of all the cuts, but we have to maximize this to find out the MaxCut problem. So we have to take the maximization for all the combinations of this x values, and we will get the maximum weight out of this expression, right? Or if the weights are 1, then we will get it equal to the number of edges, or we will get, even to that also we can say as the cut weight or the maximum cut weight, even if it is, even if the weight of the edge is 1, right? In only point is that if the weight is 1, it will be equal to the number of edges, right? So therefore this is a 0-1 quadratic optimization problem, and this this combinatorial optimization problem we have to actually formulate in such a way. First of all, we have to map this problem to the classical Ising model, and then we have to implement this problem onto a quantum computer. So we will continue with this in the next lecture. Thank you.